Now let's continue on with this notion of isomorphism, which we represent by this symbol here. And I want to talk a little bit more about how we show that two graphs are isomorphic, that as we did in the last little video. So the first thing you want to do is to state a vertex matching explicitly. Now I'll call that an isomorphism as well. Right, so that's a one-to-one correspondence of the vertices in graph 1 and the vertices in graph 2. So it may just be at the start that that's just a conjecture on your part. You don't know for sure. You're going to try. So you state that one-to-one correspondence, write it down, label it isomorphism, and then you have two choices at this stage, at least to the extent that we're going to deal with isomorphism. One is to do as we did in the previous video, and that is to check adjacency for each pair of vertices in G1 and the corresponding vertices in G2 to make sure that you have adjacent vertices in V1 correspond to adjacent vertices in G2 and vice versa, right? So you've got to do it in both directions just to make sure that you get the check. So just going from V1, there'd be N choose 2 checks. This should be a V1, but it would have to be the size of V2 if they're going to be isomorphic. That's kind of tedious, and it's not as clean to go through and write it all down. A lot more writing than the following way. The second way is to demonstrate using a specific order for each of V1 and V2 that would correspond to the vertex matching. You're going to order the vertices according to the corresponding vertices in the other graph. The adjacency matrices are the same. Show the adjacency matrices are equal if you use a particular ordering the vertices in the two graphs. Now you have to use an ordering that works, that corresponds to an isomorphism, because it's easy to get isomorphic graphs that have different adjacency matrices if you don't order them in a way that corresponds to the isomorphism, the matching that would be an isomorphism. It is the second way that I think is the easiest to write down, because in the first way it's often real easy to leave some things out. So let me show you an example where we do something like that. So let's take a particular graph that looks like this. Maybe this is our G1. So G1 looks like this. And I'm going to draw a cross piece, but it'll have a couple of vertices on it like so. So we'll go ahead and label this A, B, C, D, E, and F like so. And G2 will start off with a pentagon shape like so. And I'm going to label the vertices on this R, S, T, U, V like so. And I'm going to add one more edge on the inside like so. And let's make that a vertex right there, which is a W. So these may or may not look isomorphic to you. I mean, they certainly don't look the same, but are they the same in some way? Well, a way to focus your attention when you're looking at graphs, trying to see if they're isomorphic, is to pay attention to things like the degrees of the vertices. Most of the vertices in both of these graphs have degree 2. See, those are all degree 2. So it has 4 degree 2 vertices. That is not. That's degree 3. 4 degree 2 vertices, and this one has 4 degree 2 vertices. Yep, sure enough. And then it has these 2 that are degree 3. So you know, maybe focusing on these degree 3 ones and what goes on with them would be helpful. So if we look at the degree 3 ones, then as we go from one degree 3 one to another, thinking about that, in the one case, if we go this way along here, we've just passed through one other vertex of degree 2, and if we go this way, the same thing is happening, one other vertex of degree 2, but if we go this way, we pass through two other vertices of degree 2. Now in this graph over here, a similar thing is happening. These two roots, as we go from B to D, we pass through one other vertex of degree 2. But if we go this way, we pass through two of them of degree 2. And so that maybe gives us a way to match them up. And so I'm looking at, let me go ahead and write down the matching or isomorphism, because these are in fact isomorphic. So the isomorphism is the matching. So there'd be A, B, C, D, E, F, just to make it easy for me to read. So what I'm suggesting is that we'll go from B to D by way of F and E. So that would mean that that would correspond to going from S to W by passing through R and S to U by passing through R and V. S to U passing through these two right here of degree 2. So that would mean B would correspond to S in this scheme then. And then we go, B goes to F. F would correspond to R. B goes to F. I'm going this way right here. And then next I'd come up with E, and E corresponds to V as we go around like so. E corresponds to V. And then we end up with D here, and that corresponds to U. Okay? So that gives us a correspondence there. Now how do we hook up A and C? Well, we'll do the same thing. Let's go from B to A, then to D would be the same as S to U by way of W. So let me get a green in here. So I'm thinking going that way, and that's the same as going that way in terms of having a pathway that passes through 1 degree 2 vertex. Now you could have said, well, why don't you do it this way, dashing it like that, and that would correspond to this one here. But could you have done it so that C corresponds to T? Could you have done it in reverse, the reverse of those two? And the answer is yes. That would work as well because of the symmetric aspect of those two pathways. So there's our isomorphism. Now to show that's actually an isomorphism, we would then create the adjacency matrices of the two graphs. And so I'm going to do that right here and write down, let's do that one in the back. So AG1, the adjacency matrix of G1, using the ordering A, B, C, D, E, F. I'm going to have to go down a little bit, and A, B, C, D, E, F up here. So A is adjacent to B and D. B is adjacent to A and C and F. ACF, right? ACF. C is adjacent to B and D. D is adjacent to CEA, A, C, E. That's D, right? E is adjacent to D and F. And F is adjacent to B and E. Right, so that's what we have there. And then you do the same thing for AG2, but now use this ordering here. So the ordering I'm going to use here is W, S, T, U, R, UVR, sorry, UVR. I'm going to have to squeeze this down here a little bit more. W, S, T, U, V, R. And let's see, W is adjacent, that's W right there, is adjacent to S and U. W is adjacent to S and U. S is adjacent to R, T, W, W, T, R. T is adjacent to S and U. U is adjacent to three things, T, V, and W. Whoops, W. V is adjacent to R and U. And R is adjacent to S and V. All right, take a glance and you'll see that in fact those are equal. So a conclusion in a sentence, since AG1 equals, as a matrix, AG2, corresponding entries are equal, G1 is isomorphic to G2. And that's how I would express it as well. Okay? All of that is what I would like to see if you're showing two matrices are isomorphic. So I'm going to talk next about how to show that matrices are not isomorphic, the kinds of things you would do for that. But I think I'll stop this video and then open a new one for that.